Hello, friends, and welcome to part 3 of Machine Learning with Cats. Hey, yo! Srivanik, it's good to see you. Welcome, welcome. Happy Wednesday. I am very, very pumped to be here, and I hope you are too. Today, we are really, really going to get flying. I think I say this most Global Hack Weeks, but at least when I do a week of streaming, the beginning is always pretty similar. Like the first day is always intro to Python or re-intro to Python, and we change it up a little bit. You know, we have different things we focus on, but it's kind of the same stream. And then the next day is usually like, okay, let's try to do a simple model. Like it's half the time it's linear regression. And then by day 3, then we start getting into the, okay, what wacky things can we do just for this project? And we've got some fun stuff. But let's see. Okay. So we know we do beverage check. Let me know in the chat what beverage you're currently drinking or recently consumed. I have just the absolute privilege of drinking not 1, not 2, but 3 cups of water because my boyfriend loves me very much and wanted me to stay hydrated. And so if I don't have to pee by the middle of the stream, something is wrong. Ooh, coffee. Ooh, okay. So I'm curious, what kind of coffee are you having? Just sort of like black coffee? Is it instant coffee? Are you having a latte? If you're new to Global Hack Week, or if this is, the first or second time tuning in, you may not know this, but most Global Hack, well, not most, half of the Global Hack Weeks I'll do like a coffee stream, a dedicated coffee stream where we just make coffee together. And it's always a good time. So whenever there's coffee on stream, it's a blast. A latte, lovely. Micah, good to see you. Hello. Welcome back. So fun stuff today. We're going to do a little bit of a recap and just touch back again on our Kaggle. Good old water. There we go. Cheers to that, friendo. And then we are going to look at, the most exciting thing is we're going to do a little bit of data pre-processing. Yesterday, we did some pre-processing on our tabular data, but today we're going to do some pre-processing on our image data, which is very fun. And then, that's kind of the less fun part. And then we're going to look at dense neural networks, and we're even going to dip our toe into AI explainability, which is something that I think more and more I see us doing, sort of focusing more and more on that, not only in this stream, but in future Global Hack Weeks and in a discipline as a whole. I think that AI explainability and interpretability as sort of these 2 pillars are things that are certainly not going to become less important. So exciting to dabble in that some more. Ooh, Uji loose green sencha tea. That sounds very tasty. I am usually not a big tea person. I historically have been into coffee, but recently I've been having more tea. I think I have 1 cortado, which is, it's kind of like a latte, but less milk first thing in the morning. And then after that, I will usually do a cup or 2 of tea in the office and then have another coffee after lunch. But maybe we'll just, without further ado, get into it. Shamarie, I appreciate the honesty. Or Emily, Shamarie, same person, I believe. I appreciate the honesty. Maybe we'll try to get some earlier streams, but yes, catch the replay and hopefully, actually Friday is a little bit earlier, so maybe we'll catch you there as well. Yeah, I think that I have chosen like pretty. There are times that work for me. I think there are times that work for not that many other people. If you're on the West Coast, it's great. And then if you're in India or on the East Coast, it's like, what are you doing, Will? All right, I will see you hopefully on Friday and or on Discord or whatever. All right. Well, let's get into it. We did not have a ton of questions in the feedback form. We did have folks saying sweet things, and I appreciate that. And we did have our second vote on what color glitter I'm going to be putting on my face on Friday. And we have narrowed it down. It is now. So I'll show you the. Here, I'll show you the. Oh, you can already see it. Oh, this is not good. The monitors are off. Okay, let's actually change what monitor we're looking at. Usually the monitors just map to the right thing. Oh, that's not right either. There we go. Okay, that's the right monitor. Um, so this is the votes that we had here. We have coming in fourth place with only 2 votes, blue. Then tying for second place are green and purple, and then in first place is silver. I am colorblind, but I'm curious if anyone can weigh in. This is well, that kind of looks like a purple color, and that kind of looks like a green color, which would be interesting if those just happened to match. But yeah, so for this day, we're going to vote just on the top 3, green, purple, and silver. And then tomorrow we can vote on the last 2. Um, Otherwise, if any individuals have any questions, we can get those out of the way now. Otherwise, we can just kind of dive into it. So as always, I will drop the check-in and Kaggle links. So here is check-in. If you're here, let them know. Be loud and proud and all of that. And then here is our link for the Kaggle competition. If you are, if this is your first time tuning into this track, let me know in the comments because I am curious and maybe we can phrase this in a way that'll help you get up to speed. Otherwise, I think most folks who are with us now are probably in it to win it. Are probably here for the long haul. So, what to say? If you come to Kaggle and click on code right here, you can see what we did yesterday was this part 2 notebook, and it was based around just looking at the tabular data that we had, specifically this factor of speed. So our CryptoKitties, our very adorable CryptoKitties, every time they have children, every time they have a kitten, they become a little bit slower. And people usually prefer kitties that are faster. And maybe there's some weird purity norms baked into that. But we looked at trying to relate the price to the CryptoKitty. Oh, Stone Piker, thank you for letting me know. So question, Stone Piker, are you familiar with Python and or anything machine learning like TensorFlow or Keras? Because depending on those, if you're familiar with a little bit of Python, then I think that you can kind of just jump in and probably follow along with us with a little bit of intro. If you have not used Python before, then it might be a little bit of a rough go. But you are welcome to come to this Kaggle link that I sent out in the chat and create an account, which is where we're having this competition. I guess I should start with the big picture. We're having a competition to predict, based on the image of a CryptoKitty, an adorable CryptoKitty like this guy, how much this CryptoKitty is being sold for. So they're being sold in Ethereum, which is kind of like Bitcoin. If you're unfamiliar with Ethereum, it's another cryptocurrency. And so we're trying to predict the person that's selling this cat, how much are they asking for it? And there's, of course, some inherent silliness because, I mean, first, taste is subjective. But second, people could ask for whatever amount of money they want, right? I could say, I'm selling my house for $2 trillion. And like, that doesn't really mean anything. But that is our task. And so Kaggle gives us a platform where we can code up our machine learning solution, we can train our model, and we can use it to make predictions. And ultimately, we can all end up competing on the leaderboard here. Ooh, this is very exciting. We have a few better than the default predictions. So we've got 2 folks that have poked out in the leaderboard, and then a few folks that are a little bit lower. But so for today, you can come click on the code tab and then come down to, we're going to start with resizing our images. Okay, radical. Well, if you have any questions, I'm super thrilled that you're sticking around. If you have any questions, let us know, and we are happy to kind of help you along if there's anything that is confusing or unintuitive. So our 2 main priorities for today are doing a little pre-processing on our image data, and then really diving in with some stronger machine learning methods in this part 4. So part 3 and part 4 are going to be sort of where we're hanging out. So let's start with part 3. Yesterday we looked at tabular data, which on the one hand, there was a little bit of cleaning up we had to do. We had that speed string that we needed to turn into a number of minutes. And that required it required a regular expression, some regexing. And then we also had our our price contained commas. And so to turn it into a number that Python was happy about, we had to remove those commas. That was not really a big deal, but that was something. But so now that we're getting into image data, we have to get familiar with our image data, what it means, and how we can mess around with it. So I will drop the link to part 3. And everyone is going to want to click, for me it says edit, but yours will probably say copy and edit. And that brings up our Kaggle notebook, where we can code along and sort of see our results in real time. So we are going to also, is this? I just want to make sure that folks, when you click through, does your first cell look like this? Does it say pandas, PD, CV2, and OS? I just want to make sure that the most recent version is public. I think it should be. But so the main goal here is to resize our images so they're a little bit easier to work with. So far, everything that we have done, like all the code, has run basically instantly. When you get to building these bigger models that have more parameters, suddenly the size of the data you're working with really matters. And if your files are too big, things can take a really, really long time. And in fact, I think Kaggle actually places a limit that your submission has to run in, I think, 3 hours. But honestly, for our convenience, like 3 hours is way too long. Ooh, okay. Thank you so much for telling me this, Red Nitro. I think that means I need to make a new version public. That is such helpful information to have. Part 3, resizing our images. Let's see. Does this have it should have a version on it. Yeah, so everyone apologies if I convince you to click the wrong button. I guess it doesn't. It's currently running, so it doesn't have a version, but on mine it says version 6. Apologies, this is not the most graceful moment to deal with this silliness. Okay, if I come back over and look at code, and I click on part 3, resizing our images. No, that published version there. I don't know what. Oh yeah, this is version 5 of 6. So no, yeah, that is totally a. I mean, it should be mostly the same with just a few edits. But my new one should publish in a second, and then we can all be on the same page. It is taking a second to load. Okay, well, it should be. I mean, it should be basically the same. So if you notice any differences, let me know, and I'll let you know what's going on. I think I just cleaned up a little bit of it before I published, or after I published, I guess. But so we should be importing all of these things. There should just be some extra stuff. Anything that you don't see on my screen, you are more than free to delete. Or you can just hang tight, and in a few minutes, this should be published. Oh, it looks like we can actually see the progress here. And yeah, okay, we're about a third of the way done. So, so the packages that we're actually using, and apologies for the old version being published, are pandas, which we've already used pandas. That's interacting with our data. CV2, so CV2 Computer Vision 2 is a library that lets you manipulate images, and we'll use that a decent bit. And then OS for operating system helps us interact with our file system. So the first thing we want to do is we'll just import our training data set with pd.read CSV, and then by hitting train.head, that will, let's actually start up our session. That will show us what is in our data set. I really should publish these with all the output clear, so it's a little bit more dramatic when we run code. Oh, we're getting there. We're getting there. It's not taking that long. Okay, cool. So in our training data set, nothing has changed from yesterday, but we have our ID, our price, the speed string that we were looking at yesterday, and then a path to our image. Technically, this path is not particularly helpful because it's the path from inside the image directory. So we have, or it's inside the images directory. And so inside the images directory is another images directory, and then that's where our data is. So just know that the image path here is not the most useful thing in the world. But if we grab this images/images path, so literally I just came and clicked copy right here. So copy here and then paste. We can create a variable called image directory, and we can use a function called os.listdir. So it's literally just listing everything inside of our directory. If I hit run, we get a very, very long list. So that's why I just did, let's grab the first 10 things just to look at them. But so the first 10 things in the output of list directory are 10 different files. And you'll notice that these are not actually sorted in any particular direction. In the viewer here, it sorts things alphabetically. So it starts with all of our zeros, and then it goes, it works through our zeros up to our ones and so on. But our list, when you do os.listdir, you are not guaranteed any particular sorting. If we wanted to, we could sort them ourselves, right? We could just say, I believe sorted accepts a list. It might do it in place, though. That might be... No, okay, there we go. So if we sort the output of list dir, then we get then we get the sort of the same view as we have over here. But we just know that we can get a list of all of our individual files. So we can just grab one of those files. So this was, I guess, before I sorted. I wonder if I get the same thing. But let's actually grab the first one here. And we can use os.path.join. Now, people ask, what does os.path.join do? And it literally just adds a /. Oh, hello, Adam. It's so good to see you. Adam, we're having lots of fun with kittens today. You should stick around. Boom. Look at that. Look at that cat. He's very mad at you. That cat is upset. I don't know what about, though. But it's good to see you. Yeah, no, that's fair. You should go to sleep, dude. You should get some shut eye. We were just talking about how basically every time that I pick to stream, it works really great for people on the West Coast, and pretty much anybody else, it's kind of a bad time. Does that mean that we're slicing? It was taking some random images. Yes. So the thing that I would call out is that os.listdir doesn't do any sorting by default. And I think this is technically true of just like direct, like in Linux. If I just pull up my terminal, also don't judge me. I use my terminal on my personal computer so rarely. But if I just say ls, which stands for list, I think I probably have some formatting that actually does. Yeah, okay. So my output is sorted, but I think by default, the default, wow, I don't know, make that big enough that people can see. Mine is sorted, just trust me. But I think the spec definition of listing a directory's contents in POSIX does not necessarily include any kind of sorting, but we can sort it ourselves if we wanted it to be in order. Yes, Michael Decane. Yes, the notebook is shared, and it should be. Oh, great. Okay, we should have the actual public version of it now. If I just want to go to, or I guess if I. Okay, great. So this is the actual notebook that we are using, and I will post that. And you should be able to click copy and edit. And you should hop in right where I am. As I'm going, updating a little bit, and I will be, at the end of the session, I will publish it again so you can get the updated version of everything that I modified, but mostly I'll stick to the script. So OSLister does not actually give us anything ordered, but we can sort it if we want. And we just grabbed that first file name. And so ospath.join. So literally all ospath.joins does is add a /. So if I just say ospath.join and I pass it A and B, there's nothing special about these. It just puts them together with a /. Now, there are some cases where this is like there actually is sort of a use case here. I believe it'll dedupe. Oh, that's interesting. Okay, yeah. So that is interesting. Okay, so it'll get rid of duplicated slashes, which is kind of nice. Um, but yeah, os.path.join pretty much just joins your files together with forward slashes, which is correct on Linux. Now, interestingly, I think it will. You can have file system specific versions of this. So on file systems that have different separators, which I think are very rare, I think pretty much everybody uses forward slash. It can do different things. But it's just a nice, elegant way of saying what I want to do here is just join these two things into a path. So we can, let's comment this out and just look at our file path. So that's our full file path, which really is the same thing as if we just copied this, it would have given us that. We have a question about where are the cats. The cats are going to show up very soon. The cats are inside our PNG files, and we're about to crack one open and look at it. So the file path is there, and now we can use CV2 to read in an image file. So we're passing in our image file, and then we have to tell it how it should interpret that file. And specifically, okay. I think this is not so uncommon knowledge, but generally we think of image data on computers as being built out of individual pixels. This is not true for some file formats, like SVGs are not pixel based, and there's a little bit of like there are a lot of different ways that you can store things, but there are individual pixels inside of your image, and each of these are comprised of a red, green, and blue color value, right? This is the sort of basis of colors on screens is RGB. But there are lots of variations on the RGB scheme. You can have RGB. You can also have BGR. I believe actually in screens, the actual pixels are arranged BGR. Blue comes first in like the lineup. You can also have a notion of an alpha value. So alpha is how transparent your thing is. So you can have a very thin sort of film over something, or you could have a very opaque image that doesn't let anything from behind it through. Right. When you're dealing with HTML, this is super, or CSS and HTML, this is super relevant. Yes, you can think of these like this is what hex values are capturing. And you can, I don't know, we could go on to a hex color picker just to like, oh yeah, there we go. So this is our RGB right here. So we could type in, 0 is black, and then 255 is the highest number. So if we say just 255 in the middle and 0 and 0 on the edges, you get basically pure green, right? And then the hex value right here translates it into hexadecimal. We can make this a little bit bigger, but hexadecimal is just sort of a condensed format of this, putting it into a different number space, kind of just an abbreviation. You could crank red up to 255, and so now you have a mixture of red and green. And then if you bring up blue to 255 as well, now you have basically reinvented white. Oh wait, not 225, 255. Now we have basically white. And then if we took away the green, then we're just mixing red and blue and we get purple. So that's your sort of very, very fast intro into color theory and RGB values. Anyway, for whatever reason, the files that I have given you are technically in BGR format, and they do have an alpha value. And so we're just going to translate them into RGB just because it's a little bit simpler. So we're going to run that, and what do we get? Well, we get a bunch of numbers, right? All that an image really is a giant array of those RGB values. And so you see we have a list of lists. So our first bracket here is saying these are all of the rows of our images. And then the second bracket here is these are all of the columns of our images. And the last little bracket and list here is this is our red, green, and blue values. Yes, this is the machine learning and NFTs session. I can give so this is session 3. And so we had a lot of context in sessions 1 and 2 that if you weren't there, you may have missed. But the idea is we are predicting the value or the asking price of CryptoKitties with machine learning. It is a little bit of like by my own admission, this was just a fun project that I thought was a good time. This is not I'm sure that some people are doing much more lucrative things with machine learning NFTs, but we're having a good time. So the thing that we get when we read an image is what would we call it? It's a 200 by, or how big are these images? It's a three-dimensional array, and the first dimension is your height, and the second dimension is your width, and then the third dimension is your color space, right? And our color space RGB is just 3, so our last dimension is just 3 long. And so I think it's a good thing just to get out of the way. That's what an image is just a bunch of individual pixel values sort of stored in a two-dimensional array. Now, if we want to actually see what our image looks like, we can actually use matplotlib. PLT has a functionality called imshow that is super convenient for taking your image data stored in this giant matrix and then just rendering it as an image. So we can roll this, or we can run this cell, and if you come down, boom, there is a CryptoKitty. So a couple important things to note. First of all, you can see this kitty has lots of colors. We have RGB. That's cool. That's important. But also that the back is now black. And if you remember looking at our preview here, the back is white, and that is because our inputs were PNGs that had some transparency to them. And when we up here read it in, scrolling all the way up, with RGBA to RGB, that basically threw away all of the transparency information. And so whenever there was no color, it just became black. So we've thrown away some transparency value, which for our purposes is just fine. So now let's look at the shape. You can just say im.shape down here, and you can see it is a 3000 by 3000 by 3 matrix. I think images are a very fun level of dimensionality, because there are some things people will talk about some systems and it's like, yes, this is like a 17-dimensional matrix. Please understand all of the dimensions. And I'm like, I don't know how to picture 17 dimensions, my guy. But 3 dimensions I can handle, right? 3 dimensions is just an image. It is, a height by a width by a sort of color depth. And that's all we're dealing with. So now to sort of prove that this is all that's going on, there's nothing special about image data. There's nothing sort of like weird about it. Adam, the flower crown is a thing whenever anybody asks for it. So yes, whenever anybody asks, hey, Will, would you mind putting on the flower crown? I rush and grab it. But yeah, I don't wear it by default. Sometimes I wear it on the last day just for kicks and giggles. So we can actually do some stuff to mess around with our image, right? So we could say, we can make a copy of our image for starters. So here we're making a red copy. And then the thing that we're doing here, so, okay, maybe we should actually take, okay. Well, you asked in this last comment, flower crown, please. I will take out my flower crown, and put it on. Boom, there's the flower crown. Here we go. It's Global Hack Week now. Okay, so this is a good question. Is the image an NFT or just normal PNG? So we kind of elided this at the very beginning. What is an NFT? Well, an NFT is generally, people have different definitions, but it is generally a thing stored on a blockchain that has some sort of blockchain backed record of ownership. But that thing is just a bit of data, right? The thing stored on the blockchain, the thing stored on the Ethereum network that is a CryptoKitty is just a random chunk of data. And actually, because you asked, and I love tangents, we can go to cryptokitties.com. There we go. And if you come over to catalog and you click on CryptoKitties down here, and let's just click on the first one. Hey, Fancy Appleby. Everybody say hello to Fancy Appleby. It's been a long time. We have missed you, Fancy Appleby. Welcome back. And if you scroll down, technically, this right here, boom, this right here is the NFT, right? This is the actual data that comprises this cat. And this is not as interesting to look at. So the thing that the people who have made CryptoKitties have done is they have built some software to turn this string that is stored on a blockchain into this much more pretty looking image, right? And so there's a world in which this might actually be more valuable or more interesting to run machine learning on. Interesting actually, it might be more useful. You might see better accuracy. But this is the rendering of that NFT data is what we're actually dealing with here. So yeah, here's CryptoKitties. I'll drop the CryptoKitties link. Fancy Appleby, how have you done? How have you been? Also, beverage check. What are you drinking? I'm drinking 2 cups of water simultaneously. Sunny, hello. Hey. Grass jelly milk. Okay, it feels like you just like clicked a random word generator 3 times, because that seems just like a wild thing to be drinking. But if you are in fact drinking grass jelly milk, tell me more. I'm very interested. Is that like a is that like a milk tea? I don't know. Tell me more. You have to accept that just like if I don't know what grass jelly milk is, that is a bizarre combo of words. I'm sure it's tasty. So that was okay, cool. Oh, okay. So it's like I guess I don't grass and milk in my mind. That kind of makes sense. Like tea, grass, same category. We put milk in it. Okay, valid. Well, it sounds delicious. Now I'm gonna look up grass jelly milk. Oh, okay, yeah, absolutely. That looks very tasty. I don't know if that's what yours looks like, but sounds delicious. Right on. So that was the response to are these NFTs or just regular PNGs? And the answer is like, what is an NFT, right? An NFT is just a string of random bits on a blockchain somewhere, and then people can write software to render those in a way that's pleasing. And so yes, the thing that we're looking at is the rendering of an NFT, not the data on the blockchain itself. I think this is some context I shared on day one, but I'm not really a big Web3 guy. I actually I own a CryptoKitty, which would be an interesting thing to talk about maybe on Friday. But I'm not really a big Web3 person. And so when I got the prompt, hey, we'd love you to do a stream, maybe machine learning plus Web3. And I was like, you know what, I'll do machine learning and we'll take inspiration from some NFTs. Okay, so we have a copy of our image. And we're going to do some more slicing. So we looked at slicing a little bit for lists, but I don't think we really looked at slicing that much for arrays. So we can create a 2D array. Let's say 0, 0, 0, and then 0, 0, 0. Oh. So here we have for the sake of example, here we have a 2-dimensional array. Let's call it X. Let's see if that works. Oh, we need to use an equal sign. Also, if y'all can hear Darwin's a very mouthy lad. If it's coming through the mic, I can close the door. But much like Adam, when I close that door, this room becomes very, very warm. Okay, I guess we have to import a NumPy. You ever realize you hadn't imported NumPy and you're like, really? I've run like several cells here and NumPy hasn't come up. Yeah, Adam, you've missed a lot of streams. I think this is the second stream that I have brought Darwin out on cam. If he comes up to the office, I will show you. But yes, there is a dog. His name is Darwin. He is the most perfect boy, and I love him. Okay, so here is our. Yeah, okay. Sunny was there. Sunny saw. I'm not lying. Okay, Adam, you always say that you're going to sleep, and then you keep checking in. So I don't know what to believe. Okay, so we have our 2x2 array, and how do we do slicing on this? Well, obviously we can just do sort of regular slicing where we say this would take us from 0 to 1, and if we do that, or if we do 0 to 2, this gives us the first 2 rows. So it kind of treats our array just along sort of like the first original axis. And so saying give me everything from 0 up until 2, it gives, okay, the 0th row and then the first row, and then it leaves off number 2. But an interesting thing that that specifically NumPy arrays lets us do is that we can slice in multiple dimensions. So I can add a little comma here, and I can say, okay, I'm getting the first 2 rows, but what if I actually want the last 2 columns? So here, to make this actually clear, well, actually, let's do this. Let's say, because we can actually make an assignment here. So if I said the first 2 columns, the first 2 rows equals 1. Now we've just edited the first 2 rows. And now, what if I say I want to get of the first 2 rows, I want the last 2 columns. So I could say starting at 1 and going forward. So now I'm just getting this top 4. But if I assign this a value of, let's say, 3, and then we look at x again, now I've just isolated. Let me zoom in one more tick. It's kind of obnoxious, but here we go. Actually, this might be too zoomed in. Let me know if this is okay. But so we have isolated the first 2 rows and then the last 2 columns here. So we are slicing in multiple dimensions. Let me know if slicing in multiple dimensions is a lot. It honestly is not something we're going to use a ton. It just is kind of an interesting tangent that you can slice in multiple dimensions. And so here, with this slice, what we're doing is we're saying, give me all of the rows and all of the columns, but just the first RGB value, which in our case is red. Or yeah, I mean, the first RGB value is red. Adam, I will attempt to send you some dog pics. So if we add 150 to just our red value, we would expect this to make everything a little bit more red. And so now we can IM show our red copy, and it's thinking about it, and boom, there you go. Everything is just a little bit more red. If we wanted to crank up the red value even more, we could say 250, and that should be like a brighter red. And there you go. Now everything is even brighter. It's actually, that's a little bit interesting. It kind of looks like when we went up to 250 that the cat itself became almost less red. Maybe it just is less red in comparison. It's like an optical illusion. If we go back down to 150, yeah, it certainly looks like the cat is actually more red when we add 150. That's interesting. Oh, I guess values that are already above 250, it might start interpreting those differently. That's interesting. Anyway, you can go and mess with individual pixel values. Ooh, actually, one more thing I want to do is adding noise, because I think that's kind of fun. So what if we we have our red copy. What if we generate a random, oh, doesn't this add to R and G? So I will say, I'll confess I'm colorblind. And so if you're like, well, no, clearly that's both adding R and G, I'll believe you. So the idea here is if we just, so we can look at, if we do this, we're getting basically all of the individual pixel values. And then if we add just 0, so you see here, we've made all of our red values 150, and then our green and blue values are still at 0. And if we just say 0, then we just get our red values. If we just said 1 here, we should just get our B values. And then if we just said 2 here, then we would just get our blue values. And so you could change this up, and you could say, okay, what if we instead, what if we upped red, and then we added just 100 to our blue values. And so then you would expect to get something very purple. And okay, yeah, it looks different now. We've now mutated more of the things. But so now I want to take this and actually add some randomness to it. So we can do np random, let's say random, and we should be able to say size, and let's call the size, let's say 3000. Actually, we should just call the size the shape of our current image. So we can say im.shape. And this should give us a random noise filter. And okay, great. So this is the same shape as our original image. And we can just add this to our image just to make it like a little bit crazy. But let's actually divide this by, we don't want it to, we still want to see our cat. So let's divide this by 10. So this will just give us a little bit of randomness. And so now, if we add this to our red copy, noisy red copy, and if we PLT show this, then we should see something with just some snow, some kookiness. Whoa. Okay, well that's a lot. Oh, I guess we already messed things even more here. What if we go back to our red copy just being, or maybe even, well, let's try this. Oh wait, actually, I know what's going on. We're adding a float, and so we're turning this into a float value. And what we really want to do is we really want to turn this into an integer. So instead of random, let's say rand int, and let's give it a range of between 1 and 50. So we're going to generate a random number between 1 and 50, or 0 and 50, and we're going to add that to our color space that's 255. Okay, so we generated the thing was that our original data was that doesn't look particularly noisy. I guess part of the issue is this is such a high resolution image, and so when we're updating it pixel by pixel, it sort of all blends together. So what if we increase the noise to 150? Should get more chaotic. Okay, you can see that. That's a little bit more chaotic. And then as we get up there and we say like 200, then it should get like very, very like blurry. Okay, yeah, so we added some noise there. That's fun. But this is all okay. We spent 40 minutes on this. I'll pick up the pace a little bit, but this is all a little bit beside the point, because what we really want to do is we really want to compress our images, right? So right now our images are 3,000 by 3,000, but we can make them a lot smaller and still have basically all the same information, right? We could still reconstruct a more complex image from a simpler one. And so let's take a second to just understand like where the cutoff point is, where we start losing like super useful information. So we're just iterating through cutting it down to, it starts as 3,000, 3,000 by 3,000. We can try cutting it down to 2,000 by 2,000, 1,000 by 1,000, 500 by 500, 200 by 200, 100 by 100, 50 by 50, and then 20 by 20. So CV2 resize takes an image and then the new height, and we want to make it both the same height and width here. So we'll just use H twice. And then we can print out a title of it and then actually show the resized image. And this will just give us sort of anecdotally an understanding of, okay, yeah, at 2,000 by 2,000, it looks like, at least to me on this screen, like identical. 1,000 by 1,000 also looks identical. 500 by 500, if I get really close, maybe I can see some difference, but it still looks like we basically have all the information. 200 by 200 for me is where I notice, okay, it's a little bit pixelated, but I can still pick out all the features, right? Like if you showed me this, I might think, oh, we're playing like a 90s pixelated video game or something like that. And that would like I wouldn't say this doesn't look like a cat or like I can't make out any of its features. Shivani asks, is it changing the size of the image or the pixel size in image? This is a great question. So it kind of has to do both. We could look up and I think there are actually different ways you can use it. But so ultimately you can actually look at the axes here. And so like this top one, it ranges from 0 all the way down to 2,000. So 1,750 and then 2,000 is the next number. And then this just ranges from 0 to 1,000. And this guy just ranges from 0 to 500. So the actual matrix is getting smaller. The like number of pixels in there are getting fewer, but it still needs to make some selection about how to select what pixel. And usually it does sort of an average of, if you're scaling it down, it'll be like, well, what are all the pixels near this final pixel? And I'll average all of those together is usually sort of how the math works out. But there are different clever algorithms. So it is genuinely changing the size of the image. And then, of course, we're just rendering the image big again. So the idea of like, well, how many pixels are there? Like, actually, here's an interesting thing. I think can we download? Can you not down? I suppose we could just save it. Like if I just opened these up on my computer, by default, they would come up at different sizes because they do have different numbers of pixels. IM show just does resizing sort of on the fly. So you can see, even as we're getting more pixelated, like the image is rendered at a bigger size, even if there's less data inside of it. And I understand that is like kind of a trippy thing to think about. But so our axes are just kind of scaled up, if that makes sense. And then when we get to 100 by 100, this is where I suddenly am like, oh yeah, I don't know if that really looks like the same thing anymore. Like that's like this is still cute. I guess that's one way of putting it. This is cute. This is still cute. This suddenly, I'm like, I don't know, man. And then weirdly, when we get down to 50 by 50, it kind of looks cute again. But clearly, a lot of information has been lost, right? And then, okay, 20 by 20, like clearly, like I couldn't even tell you this is a cat at this point. It looks like a little gremlin, you know? So 200 by 200 seems like a reasonable thing. So what we can do is we can just get our, create a new directory called resized. So all of our input data is from up here, but then we have a caggled out /working directory that is where all of the stuff that we're outputting can be saved. And so we can create that directory. In fact, if we just run this little bit, you can see resize just showed up here. We now have a directory. And now we can just come through and we can actually get all of the images in our image directory, join them together, read in the files, and then resize them to that 200 by 200, and then just write them out to our resized directory path. So to this resize thing. And then we can use this data in the future and just have it be a little bit sped up. So I'm going to kick this off, and you can see that it runs pretty slowly. And this is why actually I actually ran this before. It was running earlier. And so now we can immediately move on. This is like when they put something in the oven and then and they already had it baking, and so they pull it immediately out on sort of the cooking show. That is what we're going to do here, because I mean, it'd only take like 5 minutes, but I already have it ready. Srivonic asks a question. It may sound silly, but if an image is turned to an NFT, and if we are doing something on that image, does that make any change, like on the NFT or something? This is not a silly question at all. So I'll come back to this previous question of like, are these PNGs like really NFTs, or are they just regular PNGs? And I would say like all PNGs are regular PNGs, right? There's no image file. There's no image file that is an NFT. If you come on to CryptoKitties, just because it's kind of a fun little example. I'll put back up the question here. So the actual, the actual data that is on the blockchain is right here, which is kind of cool. And this is the real NFT. And to actually edit the NFT, we would have to, via whatever rules there are, which I won't really get into, we would have to modify this data stored on the blockchain, on the Ethereum blockchain network. And we don't have the power to do that because we don't own this thing, and we wouldn't actually be able to. But we can see what it renders like. And so for our purposes, we have just basically took it a screenshot of this, right? I mean, I went and I downloaded some of these images into a data set, and so we're not directly working with the NFT itself. We're working with a sort of a rendering of the NFT. This is like, I don't know if you remember, there was a string of jokes about how like someone spent $100,000 on a Bored Ape Yacht Club NFT, and then like people would just like go and like download the JPEG of it, and they were like, oh no, don't steal my NFT. And it's like, my brother in Christ, it's just an image on the internet, like we can just download it. Anyway, a little bit of silliness around NFTs. Okay, so I have grown tired of watching this run, so we'll just X out of it. But now, if you come back over to, this is the sort of we can refresh it, but this is sort of the public view of this notebook. And if you go to output, you can see they're not going to render pretty, I guess. But we could download it, I suppose. There you go. And actually, notice this is a lot smaller, right? This is by default. And I can zoom in, of course, and we can see that it's, that it's a little bit pixelated. But but that is in the output directory there. Yeah, absolutely. No, thank you for the questions. It is always good to engage. Okay, so now we can come back over to if we come back over to our homepage and we click into code, and we come over to part 4, image regression with Keras. So now we actually get to throw a giant neural network at this. Let's see. Michael asks, so that string seems pretty short. Are NFTs usually storing the entire file metadata? So I will confess, we're approaching sort of the border of my my understanding. I will say that it's like on the Ethereum blockchain, the actual image data is not stored. I mean, I'm down to sort of engage with whatever questions you have, even if it's like, even if I'm not an NFT expert here. But so for CryptoKitties, if we go back, I really should have just had that page saved because we keep going back to it for an example. But as you come down here, so this is not that much data, but if we click on the little zoom in thing, you can see that if you chunk that up, so first of all, each of these numbers is represented by a binary. If you zoom in there, so an 11 is represented by 0, 1, 0, 1, 1. That's binary for 11. And then a chunk of these is what they call a gene. So the chunk of 4 things here encodes what its fur is going to look like. So it has a Himalayan fur shape. And then this next chunk of little bytes, I guess this is technically, I guess this is 2 bytes, encodes that it's going to have the jaguar fur pattern. And then this next 4 bytes encodes that it's going to have a chestnut eye color. And you can kind of go on. And they even have a lot of data that is currently not being used. And it seems like at some point they will make use of that in some way. But so just these things that show up here in just these relatively small amounts of data are enough to render an image like this. So it's not storing all the individual pixels on the blockchain. It's just storing like this is like when you play Sims. If I don't know if I'm dating myself. It's been a long time since I've played Sims. I don't know what other, or like if you make an avatar and you have like 3 options for the hair and you have like 6 options for the height. And so it's not actually storing all the individual pixels. It's just storing like, well, of these 16 fur options, which one are you? And then it is their software that is rendering it into an image. And I hope that makes sense. But yeah, no, you're totally right that it's like this is a much smaller amount of data than the actual image that we have. Cool. Okay, so we can jump into part 4, image regression with Keras. And this is where, at the end of this, we should actually have a notebook that is outperforming the current leaderboard. In fact, I think by quite a bit. So we talked a little bit about this last time, and I'll get a cell running just because. But there are lots of different kinds of tasks that you can do in machine learning. And I'm going to fix my typo there. Image. Boom. So there are a couple different categories. There's like what kind of data you are using and what you are trying to do with that data. So a very classic type of data is tabular data. That's what we looked at yesterday. And the task that we had was regression. We were trying to predict sort of a real value, so some number between 0 and infinity. You have lots of different kinds of data like text, audio, images, video. So another interesting example is like on some level, the thing that ChatGPT does is it takes text as the data it's working with, and it is trying to classify of all of the possible words out there. It's trying to classify what is the most likely next word. What next word should I say, right? And so one word gets classified as correct, and all the other words get classified as as not the right word to say right now. That's like obviously a vast oversimplification, but that's sort of what we're dealing with. And different types of tasks. I think we talked about this yesterday a decent bit. But the main tasks that you see come up are unsupervised learning. So that is stuff like clustering. If you have a bunch of customers in your database and you're trying to segment them into, oh, these are our Trader Joe's soccer moms and these are our bubblegum punks and whatever. That could be a clustering job. Reinforcement learning, again, is where your algorithm can kind of interact with its environment and poke and prod things and learn for itself. And then prediction is this idea of supervised learning, where you have some labeled examples and you are trying to predict based on an unlabeled example. So if you had a bunch of images of cats and dogs and you classified them, and then I took a new picture and I asked the algorithm, well, hey, is this a cat or a dog? That would be supervised learning. And under supervised learning, there are these two tasks of classification and regression. And I threw out one right there, image classification. Is it a cat or a dog, right? And it turns out that when it comes to images, classification is just a much more common task. And image regression is not actually that common. So going from unimage to a real valued number, not like a classification, is not the most common thing. Anyway, I thought it was neat just to spell out that sort of map of all the things that you can do, and that image regression is like just not the most common. Anyway, today we're going to do image regression because we're going to look at that image data and try to predict that real valued number from 0 to infinity. As always, we can import some libraries. NumPy is just going to be our library for dealing with our big matrices. Pandas will import our training data again. OS for manipulating images in the file system. CV2 for reading in image data. TQDM. I don't know if we talked about TQDM, but it is a nice little loading icon thing. So when you're looping through something, when you're looping through a very long list, then TQDM can give you a sense in real time of how far you've made it through the list, which is kind of nice. And then our trusty dusty companion, matplotlib. So let's start by reading in our training data and going for our grabbing our images from our resize directory. So you can see here that I have both our sort of official data set, and then I also have the output of our notebook. We have output into a directory called resized. And great question. How can we find these notebooks and the past ones as well? So we'll take a quick break to talk through that. If, let's see, if you come over to this link right here, you should see a screen that looks like this, and you should be able to click over to code, and you can see all of the notebooks. So we have part 1 was our Python crash course. Part 1.5 was just making a submission. Part 2 was our simple model we built yesterday. And then part 3 was what we've already done today. And part 2 is what we're doing now. Or sorry, part 4 is what we're doing now. Great question. So back to image regression. So here we are. I'll run the cell. But so we're importing our training data frame. I actually don't know why we're doing that. But so our directory over here. Oh, that's interesting. Whoa. Our directory over here has a part 2 resizing our images, and we have all of our resized images in here. Oh, I see. We're just running over our training data here. So for every item in our training data, we're going to construct a little path. So it's our image dir, which is this resize directory right here. And then the ID, we're just going to add .png onto the end. We mentioned this, there is that, if you look inside the training DF, there is an image path. It's not actually that useful, and it no longer applies because all of our images are in this resized directory here. So that is not what we're going to use. But we can pretty easily just os.path.join our image directory and then this constructed file name. And then unlike last time, this time we'll still use CV2 imread to read an image data from our image path. But we're actually just going to read in the image in grayscale. We can go and add color a little bit later, but just for making something very simple, I just wanted to start by looking at grayscale. And then we can divide everything by 255. So by default, our data will range from 0 to 255. But it's a little bit nicer to have it from 0 to 1. And so we're just going to scale it down by 255. Then finally, this is a little bit of a weird step here, but because we made it grayscale, it's just going to be 2 by 2. And by default, the model that we're going to write is going to expect 2 by 2, or sorry, it's going to expect, I called it 2 by 2. It's going to, by default, be 200 by 200 by 3. And we're scaling it down to 200 by 200 by removing that extra dimension. And all this is going to do is just wrap it in one extra dimension, as if it had 3 different values, but we're just putting one in there. If that doesn't make sense, feel free to ask a question. Also, feel free to just let that line wash over you. It's not that important. And then we'll take this image that we just did pre-processing on and add it to a list of image data here. So we'll just read in all of our image data. And you see this is much faster than it was importing all the big ones. And that is sort of the main value proposition of our of downsizing all of our images. So now if we just look at the first thing inside of our image data, you can see there's a 2-dimensional array, but then each item inside of our 2-dimensional array is a sort of another dimension with just one thing in it, which is our grayscale value. And of course, we can render it with imshow, and we can do cmap equal gray just to get it as it actually looks like. And here we have it. We have another cat. This is cat number 0 in our data set. Yes, great question. Each element so inside image data, each of these, if I just showed you this, it's not going to be super, it's going to look silly. But so each of these big arrays is a cat, and we have those in sort of an encompassing list. Or like another way of putting it is if we went over a list and we said for image in image data, each individual image would be a cat. We can just look at like the first 4 here. So this is the first thing in that list. Oh wait, we're just seeing the last one here. This is the first thing in the list. This is the second thing in the list. This is the third thing in the list, and this is the fourth thing in the list. But each element is itself a 3-dimensional array. Cool. Yeah. I think we are, especially with image data, once you get into the world of machine learning with bigger models, keeping track of your dimensions is, I think, not the hardest problem, but it is one of the hardest problems. So if you ever have a question about wait, what is our dimensionality? Like, how big is the matrix? What's going on here? All those questions are super valid. Ooh, I'm gonna see if I have any. I think I put some throat. What do you call it? Not a throat lozenge. A cough drop. I think I hit some cough drops down here because my throat. Day 3 of streaming, y'all. My throat is going through it. Okay, I probably took them up to the bathroom where they really actually belong. So I will have to get some cough drops later. I might call an intermission in a second to get some cough drops. Oh, actually, speaking of intermission, this is a great moment to drop the feedback form. So this is feedback form number 3. It is always helpful to know how the session is going for you if you have any specific questions. And even more than that, it is exciting to see what I'm going to dye my hair. Oh, option 5 shouldn't be there. That's silly. Let's get rid of option 5. So the 3 options left are red, green, and silver. Cool. That should work now. Is this the same link? It's not the same link. That's funny. But so go and vote for red, green, or silver there. And then I guess tomorrow, we could make it on the last vote. Let me know what y'all think. We could either just have whichever one votes. Tomorrow it'll be a head-to-head matchup between the 2 winners of today. We could just have whichever one wins, or we could say whatever ratio they get, that's the ratio I'll do them in my face. So if it's like 2-to-1 silver to red, then it'll be mostly silver and then like a little bit red. If anybody has strong opinions about this, let me know in the comments. Okay, so dimensionality is important. So we have a list of all of our individual images, and then each image is a 3-dimensional matrix. 2 dimensions for height and width, and then 1 dimension for that grayscale color. So then we're going to turn that list of images into an overall array. So if you noticed, if we look at just image data, this first bracket means that it itself is a list, or maybe better yet, if we just ask for the type of image data, it's actually just a list right now. But we want to turn that overall thing into a matrix itself. And so we can do that by just saying np array, pass in our image data, and then cast that as a float. So saying as type just says, I'd like you to treat this array as if it were a float. And so now, if we check the type of our input data, we get a NumPy array, which is lovely. This is just doing the same cleanup on our price data that we had earlier. So if we run this, it removes all of our commas and then turns it actually into a float. We do the same values as type, turning our list of individual prices into a matrix of floats. So that looks good. We also clip them. So remember, this is the whole conversation about like, well, there are a few people out there that it's like, my cat is worth $2 billion. And like, they might believe that. But if there's only 2 people and they haven't sold their cats yet, that kind of doesn't mean much. And it's not like very useful to us in terms of how people value things. And so just clipping those upper values is sort of a way of addressing that. And then we can just check to see that the maximum of our labels is in fact 100. And then, as I mentioned, dimensionality can get very tricky. So just doing a reality check, this is reality check. Do our input data and labels, really, do we have the same number of input images and labels? And the answer is yes, we have 2,000 of both of them. Okay, so now we get to have some fun. Actually, I'm curious, drop in the comments if you have ever used TensorFlow and or Keras. If you have, or like, let's say if you've used TensorFlow or Keras, give me like a thumbs up or like a 1. And if you've never used them, give me a thumbs down or a 0. Or you could just say yes or no. I guess that would work as well. Okay, great. We've got some 1s and some 0s. So I'll do a little bit of an intro. So at a very high level, in fact, now that I'm pontificating, now that we're going to get into history, I will make my head big. So at a very high level, the thing that modern machine learning algorithms are is a bunch of very giant matrices that get multiplied together. That is basically you put some data into it on one end, and a bunch of giant matrices get multiplied together, and then on the output you get some sort of result. And it's the picking what those giant matrices in the middle are, those giant stacks of numbers, picking what those are is sort of what training is. And so there are a lot of libraries to deal with all of that crazy matrix multiplication in the middle for you. And TensorFlow is one such library. So a tensor is just a synonym for a matrix. And so TensorFlow is simply saying, we're letting your data flow through a bunch of matrices that we're multiplying together and doing some other logic around. It's not just multiplication, but like it's a lot of matrix multiplication. And TensorFlow is great at this, right? It handles a lot of the low-level details really, really nicely. But doing this process where you have all these matrices together and you're doing a bunch of multiplication, it's a pretty complex process. And so TensorFlow can be a pretty complicated library to use. So that is where Keras comes in. And Keras is sort of the way that I like to put it is that Keras turns TensorFlow into a bunch of Legos. They give you a bunch of these individual Lego layers that you can stack on top of one another to build a model in a way that is pretty simple and straightforward. And so I genuinely think Keras is like one of the like in the trade-off of like how much power do you get and how much complexity do you have to deal with, Keras sits at this point where there's not that much complexity, but you can get a lot of power out of it, as we will see a little bit today and a lot tomorrow as well. So that is my intro for TensorFlow and Keras. So you'll see that we import TensorFlow as TF here, but then basically everything else is just going to be TF.Keras and then some stuff inside the Keras model. So inside TensorFlow, there's a thing called Keras. Inside Keras, there's a thing called models. Inside models, there's a thing called sequential. And so a sequential model, a sequential Keras model, just says you just kind of have one vertical stack of Legos, and at every step, data is going to flow from one step into the next one, right? And there is so this list right here, this is our list of sort of Lego layers that we're passing in. So let's unpack those. What are our Lego layers? The first one is flatten. So this is tf.keras.layers.flatten. And that just takes whatever data you have and it squishes it down into a single dimension. So for us, remember our data right now, if we just look at our input data here, or really if we look at input data 0.shape, remember our first dimension is just the list of individual images. So we're 200 by 200 by 1. And really, we're just, at least for this model, we're just going to squish that all down to, it would almost be as if we were just squishing it down into a single layer of all of our pixels, right? And the reason that flattening it is nice is because then it's a single vector that we can use all additional different kinds of layers on. And the sort of classic kind of layer is a dense layer. So a dense layer is called a dense layer because everything is densely connected. Everything at one layer is connected to everything at the next layer. There are some layers, some kinds of layers that are a little bit more selective than that, but a dense layer is sort of your basic first kind of layer in a neural network. In fact, if we just look up dense neural network, an image will probably be pretty enlightening. Okay, so here's a good example of an image where you have all of your inputs here, and each one of these has a connection to every neuron at the next level. So a dense layer is going to play nicely after we flatten all of the data. And then units right here, we're passing in units. Flatten doesn't take any parameters because you basically flatten everything in the same way. You just take all the data and you string it along into one line. But with our dense layer, we know it's going to be taking everything from the previous layer, but we don't know how many things it's going to be outputting, right? And because we know that we're trying to predict a single number, our last thing is going to have to say units equals 1. Like that's always going to be sort of the last layer there. So here we have defined our sequential Keras model, and we're storing that in a variable called model, or maybe even we'll call it simple model. And what we can do is we can take this simple model and we can compile it. So defining your model doesn't get it ready to sort of ship onto a GPU. But by compiling it, we add a couple of additional pieces of information. So the first one is loss. And remember, for our competition, our target is to minimize mean absolute error. So mean absolute error is, remember, you take how far off you were with each guess. You take the absolute value of that, so negatives and positives are both positive, and you just average it all together. And this basically tells you, on average, how far away from the right answer was I. So if we go actually over to our leaderboard, right now the answer is we're all like 38 Ethereum away from the right answer. I'm very pleased that some people played around a little bit and got some better results there. So that is our loss, and that is how our model is going to know, like, if it's making progress. So our model is going to try, when we train it, it's going to try different things, and at every step, once it tries something new, it's going to say, well, hey, what was my loss? Did my loss get better or worse? And so we have to tell it, well, this is your standard for being better or worse here. And then our optimizer basically gives it the math it needs to determine what thing to try next. So every time it tries something, it's going to see, well, hey, did I get it better or worse? But it kind of needs to know, in what direction do I need to change in order to hopefully get better on the next round? And that's what our optimizer is doing. We could spend multiple weeks just on optimizers, but Atom is usually a pretty good option. I believe it sort of takes the best of both RMS prop and sort of SGD. I'd have to refresh on my optimizer math, but I believe there's a notion of momentum as well. Or I think it might dispense with momentum in favor of a beta value. We're getting deep on optimizers, and I'm actually not very well versed on optimizers right now. All this information was in my brain at some point. So then we can just take our model and run fit. And fit is where the actual training happens. So if we press play on this, we will see it takes a second to load up. You'll also see if you come up here, we should see our GPU start getting used. Oh, there we go. Our GPU is in business. Oh yeah, I forgot. Simple model. Ha ha ha. Okay, but our GPU just burst up to 15 gigabytes of GPU utilization. Love to see it. Okay, so let's come down here and see what we're looking at. So, what are we looking at? So this is all of our epics. Oh yeah, so I didn't talk about fitting. So for fitting, we have to provide both our input data and our labels. This is of course what it sees when it makes a prediction, and then what its prediction is. And then we also have to tell it a number of epics. And so a number of epics is how many times to run through all of your data. So one epic is running through all of your data once. This is sort of like if I give you a textbook to read and I tell you read this textbook 10 times. That is sort of 10 epics there. Then batch size, this is like how many problems does it do in one sitting. It's sort of like if I say a batch size of 16, I'm saying do 16 questions and then come back and I'll grade you, and then do 16 more questions. So that's sort of like the how many questions are you answering at a time. And then verbose equals 1 just means we're getting this output here. I believe you can actually increase verbosity and get like more information. You say 2. Okay, yeah, we're getting each individual step here, which honestly is kind of, it's actually not that much more information. Interesting. But verbosity 1 is usually a good bet. And then the output here, so obviously you could see as the training process was running, but you can also see this loss number. So the loss is our mean absolute error, and it started at 12. But then as we kind of came down the pipe, it worked down to 11.57. Now, again, this is on data that it has already seen, and so we shouldn't get too excited. But 11 as a loss is way better than 38, right? So there's some reason to be sort of excited about that. So early steps, but like kind of promising. This model that's pretty simple. It only has a single dense layer. Seems to be doing fairly well. Now, I want to dive into a little bit on understanding what our model really looks like and what we think it's picking up on and what it's learning. So if we do model.summary, simple model again. I changed it to simple model, and it's really biting me in the butt here. Okay, so let's give us a little bit of a summary of what our model looks like. And it shows us the shape of our data at each step. So the first layer here has a shape of 16 by 40,000. Now, 16 by 40,000, you might be thinking like, Will, where are those numbers coming from? I thought that our image was like 200 by 200, right? And the answer is yes, it was. And 200 times 200 is in fact 40,000. So 40,000 is actually the number of pixels in our, now I'm going to fact check that. 200 by 200. Yeah, okay, cool, 40,000. Y'all got me questioning myself. And then 16 is actually our batch size. Remember we said batch size equals 16. So basically when we send it with a single quiz to go and work out the answers to, we're sending it with 16 questions, and each question comes with 40,000 pixels. So that's the shape of our data. And then the other column here is parameter count. Now, this is something that I think actually is becoming increasingly sort of an interesting thing to think about, is our parameter count, specifically because people often use parameter count as a measure of sort of how big and powerful a model is. So I believe, let's see, parameter count, GPT-3. GPT-3, I remember, was being around the 100 billion, 175 billion. Okay, cool. But then GPT-4, I believe some people have, I think they maybe haven't released it, but it's like people estimate it's around 1 trillion. Yeah, okay, 1.76 trillion parameters, which is an interesting mixture of experts. Ensemble. And so compared to those, right now we have 40,000 parameters, and in comparison, that's like not that many parameters, right? That actually seems pretty small. But 40,000, in fact, 40,001 parameters. That one there is coming from a bias unit. which is not really that important, but at every step you multiply your layer forward, and you have a sort of a thing that is always set to be 1, so that you can have some additional weight there. And then our last layer, the data size, is 16 by 1. Again, it's basically returning us 16 questions that all have one answer. That's sort of the output it's giving us. So this is sort of one interesting way to think about what our network looks like. But another way we can use this is actually visualizing our weights. So parameters and weights are basically synonymous. They're like the thing that your network actually learns, right? We mentioned that that modern machine learning systems are like giant matrices in the middle that you multiply data through by to get your result. And in this scenario, we have one giant matrix in the middle that our input data is getting multiplied by, and that is our dense layer, right? The moment that you think about sort of a matrix as a function that takes data of one size and turns it into a different size, that is a moment when that visualization in your mind happens. It is like a big step forward in understanding machine learning. And so we can actually get that matrix of weights. And in fact, that matrix of weights is going to be a 40,000. The weight itself is going to be 40,000 individual elements. And we can reshape that 40,000 weights back into the shape of our picture. So if we go and we grab, just for clarity, so if we say model.layers, I'll sort of walk us through step by step here of what we're doing. Simple model.layers, excuse me. So you can see we get a list of 2 layers. We have our flattened layer and our dense layer. And we don't really care about our flattened layer because our flattened layer doesn't really learn anything. It just reshapes our data for us. So we could grab a layer at index 1, and then we could say .get weights. And that actually gives us a list of both our main weights, and then this is actually our bias unit here. And it's important, but it's not that important. We can kind of just throw it away. But this first giant array, this is the one that has 40,000 things in it. So we want to grab that. So that's our 0. And when we get this, we can just assign it down here. We're just assigning that to dense weights. So we just sort of walk through it step by step. But we have a giant matrix of our dense weights. And then we can reshape it. So if we actually get the shape of our dense weights, it'll just be 40,000. It'll just be 40,000 by 1, right? Because we flattened it. And then I really need to clear outputs because I want some drama here, you know? But we can reshape our dense weights back into that matrix 200 by 200. So this is kind of hard to see, but if we check the shape of it now, it's back to 200 by 200 just by calling the reshape function. Oh, Darwin is here again. Darwin has come and graced us with his presence, and we love him very much for that. He doesn't hate getting picked up, but it's not his favorite thing. There you go, bud. There you go. He is a perfect dog. Ooh, okay, great question. What is the reason for the brackets 0 at the end of it? So if we remove that, we actually get a list of 2 things. So we get... and if you remember, actually, this was the thing we threw out about how, hey, why is this 4,000 or 40,001? Because 40,000 is the shape of our input, and we imagine 1 weight per input pixel. And then we get this extra 1 right here. And so our weights are actually comprised of our weights and a bias. We might actually be able to find an image of this neural network diagram, maybe. Do we have any that? Oh, this one might explain it. Okay, or explain is a aggressive word. Excuse me. But if you see here, in this part right here, this is a dense neural network, and we have all of these things feeding into all of these things. And then we have this little guy here. And this bias node basically is always pinned to 1. And so all of these weights can kind of become whatever they want. And to get an intuitive understanding of why do we add a bias node, you honestly have to sort of sit with the math for a while. But the thing that it sort of lets us do is actually, we have a great analogy. It's not going to be perfectly elucidating, but the thing this bias node can do is kind of like yesterday when we were looking at based on the speed of a cat. Given the speed of the cat was like purely negatively related to price, we started out with sort of a default price of the cat, right? We said by default the cat is $100 or 100 Ethereum, and all of these things that change just reduce the price a little bit. And this bias node serves as that sort of like, if we don't get any input, if we're just staring at a blank image, what do we think, right? So that is sort of one way of thinking about what that bias node is doing. Anyway, for what I hope are obvious reasons, because of that, it's not part of our big things. And yes, so it is a list of two things: the weights and the bias. And we just want to get the sort of the weights themselves, and so we can grab it that way. So we've reshaped it to 200 by 200, and now we can take our reshaped weights and we can actually just visualize them as if they were a picture. This only works at sort of very, very small models, right? And once we start getting a little bit more complex, this will cease to become a useful way of doing things. But we can just visualize this is what the weights actually are. And this, to me, like, this is just the coolest thing in the world. Is we took a random matrix and we just showed it a lot of cats and told it, hey, like, please learn how much these cats are worth. And this is the matrix that it created. And really what this means is that anywhere where you see a very bright pixel, that pixel being bright in the original image is correlated with the NFT being valuable, or at least being having a high asking price. And so, I mean, it's a little bit funky, but you can totally see the shape of like what I might call the average cat, right? You can kind of see all the cats averaged together. And then you also have a lot of specific traits. So you can see like, oh, like the eyes, there are specific patterns in eyes that seem to be lit up. You also have like around the cat, this really, really bright space. And so one way of thinking about this is that like cats that on top of the default cat shape have some stuff sticking out, that space where things can stick out of the cat seem to have a positive impact. You can also see over here where tails often are. You can see there are certain patterns of tails that kind of show up. Anyway, it's not telling you anything too terribly conclusive about what our model has learned, but it is kind of showing you in general what patterns is it indexing on. Thank you, Nanotubular. I find this very cool as well. Let's see, is parameters synonymous to dimensions, or is it a different concept? So I will say in keeping your dimensions straight is a very tricky job. It's I think one of the trickiest jobs. There is some sense in which parameters are synonymous with dimension. I mean, one thing that like one tricky example case is that right here, a picture that had 40,000 pixels results in 40,000 parameters, but that original 40,000 pixels were originally shaped into a 3 dimensions, right? Into a height, a width, and sort of a pixel depth. And so one way you could think about it is that this flatten function took whatever specific dimension our image had and reduced it just to a dimension of the length of 40,000. So the mathematician in me is like, we really should have like really rigorous definitions for all these things. But I would say no, in terms of the dimension of like in some sense, really, we would say that the dimension and shape are the same word or are synonymous. So here we'd say that our data has a shape of 16 by 40,000, or it has 2 dimensions. And then here we'd also say we have 2 dimensions. And it's just the size of those dimensions. So the size of the dimension here is 40,000. I will also say that like these words can be tricky. Or here's another way of putting it: is in our when we reshaped our matrix into a 200 by 200 grid here, it still has 40,000 cells. So the number of parameters is the number of individual numbers inside your weights matrix. If that if that makes sense. We also often think about our weights matrix as not really having a dimension, because we will often just line it up in just a giant string. Whereas the shape of our data is something that it makes a lot more sense to say, well, this has a particular dimension. But it's a good question, and I wish I had like more instant clarity that I could give you. Okay, so something that I want to do, just because this is kind of to me a cool image, is I want to train this for longer. So we trained it for 10 epochs, but what if we trained it for 500 epochs? And at some point, it'll both be kind of interesting to see the loss over here, but then it will also be interesting to see, does it learn anything deeper? Also, actually, maybe 500 is too much. I'm going to kill that, and maybe we switch back to just 100. I'm impatient. What can I say? Okay, we're almost halfway now. And I'm interested to actually visualize these side by side to see sort of like, as the weights have updated, has anything changed? And maybe it won't change very much. Maybe I'll have to do something different to like see some development. Okay, so we can now get our dense weights again. And now I want to just copy this so that we can compare. Whoa, interesting. Okay, so this is early on after just 10 epochs. These were the weights, and these were what they looked like. And here is after a longer period of time, we get a lot of sort of more interesting patterns. I mean, for one, it looks like we have some specific pixel patterns around the whiskers. So like having a particular whisker pattern apparently is very, very bad for your value because that's very dark, meaning that the values are very, very close to zero. And then around here you have a slight darker pattern around this. Was this called like the Himalayan pattern? It might have been. Oh no, I think this was the Jaguar pattern. I think we looked at it yesterday. Anyway, this is very neat to me how early on it had not captured that much information, and then it gets sort of a lot more sort of specific ideas about our data as we train it for longer. So now we're getting up there on time. So maybe we'll do a little bit of a bigger model now, and we'll see if we can improve the. Let's see, by the end here, our loss was like 11.3-ish. So what if we just made, what if we gave ourselves a hidden layer in the middle? So here we're taking the same network, but we're saying, what if we just gave it one more layer of neurons for it to, I mean, generally the idea here is that it can understand sort of more complex relationships in the input data by giving it this hidden layer. And so here we'll say the hidden layer on the inside gets 256 units. And let's let it train for a similar amount of time. And okay, so you see, it actually is not. It's not getting that much better. And one thought is that our network is just larger. And actually, well, this is something that we could see is if we do model.summary. And you can see our total parameter count. Earlier it was 40,000. Now it's 10 million. So we have like more than 10x, more than 100x the amount of parameters we have to train. And generally speaking, as the number of parameters you have to train goes up, the amount of time you need to train them also goes up. And actually 256 is pretty high. Let's drop that down to 16. And let's give it, and actually maybe let's make our middle layer a little bit smaller. What if we made it, let's make it 64. So we're giving it 64 neurons in the middle. And then let's give it, instead of just 10 epochs to train, what if we gave it 50? So you see it's taken a little bit more time, but we are now getting into that error range of around 11. And we should see our our model summary should show us our updated parameter count. This should be smaller now. Okay, so now we only have 2 million parameters, but hey, we're getting up there in parameter count. And so our final loss down here ends up tapping out at like 11.06, which we scroll back up. 11.06 is actually better than that lowest error we got here. So by adding this in this sort of layer of neurons in the middle, we actually are able to get sort of better performance. Is it like the more time the data is trained, like as we increase the epochs, we get a clear vision of the kitties? Yeah, I mean, I think that's not an unfair way of, if we're talking about this, it's not an unfair way of putting it. And I mean, obviously there are 2,000 kitties that we're training over. And so clearly it's like, well, it's not going to see every kitty at the same time, but you kind of see a superposition of lots of kitties at once, right? And you can see, you know, it's like if you zoom in, you have like a little beard thing here, and you have like a little kitty holding something in its hand over on the left. And yeah, it's like over here, it has a pretty, I mean, the main thing that I would say is up here, there's just a lot of noise, right? There's a lot of like random pixel variation that doesn't really seem to be related to any actual traits about a CryptoKitty. And down here, things just are a lot clearer. You have patterns that are sticking out kind of more clearly. So yeah, I think the idea of as time goes by, getting a sort of clearer vision of the kitties is not a terrible way of putting it. So we made our brain a little bit bigger, and we got a little bit better performance. So something I didn't really talk about is as we were training, the training process actually output this variable called history. And that stores all this data that we saw here. It stores that in sort of a little list of sort of data tracking the progress. And so we can use our trusty dusty matplotlib to just plot that. So if I run this cell, you can see, so history has a parameter called, or an attribute called history. And inside that, it's a dictionary with all of the numbers we were tracking. And so we can track loss. And so you can see it started up at 17, and it drops down really quickly at first, and then it kind of slows down. And there's actually a little bit of noise there, and it doesn't seem to like perfectly settle. Nanotubular says, I can never tell how many layers to use / their order. Well, you have activated my trap card, my friend. We're going to actually run a little bit of an experiment to that effect in just a second. It's not going to be all encompassing, but it is going to tell us something. So, so that is a sort of interesting view. And we can see that, yeah, like the initial training that we did was super valuable. And then, okay, if we gave it another 100 epochs, like it looks like it would probably continue to go down a little bit, but probably not by much. In terms of like how much value do we get for our computational resources, like we clearly hit some point around 10 epochs where it's like maybe it's not actually it's not getting the big wins for us anymore. Okay, so one thing that I want to call out, and we touched on this yesterday, is that so far we have only really been testing our data on data that it was trained on. And this causes all sorts of issues. I know that if you've done any of these streams with me before, I never make it through a week without bringing up my favorite machine learning topic, overfitting. And the metaphor that I always like to use for describing overfitting is the metaphor of like just you taking a test at school. And the idea is, so let's say that I'm your professor, and I have a bank of 100 questions. And say that I give you that bank of 100 questions as a study guide, and you have the questions and the answers. You have the labeled questions. And I say, hey, I'm going to randomly select 10 of these to be on the test. And y'all go take your study guide and you study it, right? And you really have two options of things you could do. One is you could, really study the material and sort of use the study guide to check and kind of get a sense of what the questions will be like and really learn the material. But you could also just try to remember a bunch of specific answers, right? If it's not that big of a set, if it's just, 100 questions, your brain is big enough to store, 100 memorized question answer pairs. And it might be your best option to do well on this test to just try to memorize the answers. And so because of that, if I am a good teacher, I'm not going to do that. I'm actually going to start by divvying up my data, my question and answers. And I'm going to give you, maybe I'll give you 80% of the questions as a study guide. And I'll say, hey, I originally had 100 questions, and here are 80 of them, but the other 20 are secret. And I'm not going to show them to you until the test. And so because of that, because you actually don't know what's going to be on the test, and you know that you can't just memorize these questions, it's actually going to force you to, if you're going to get a good performance on that test, it's going to force you to actually understand the underlying information as opposed to just memorizing some question answer pairs. So this is what's called overfitting, is when you do that sort of memorization process, and our model can do it too sometimes if we're not careful. So a way to try to prevent this is what we did in our metaphor, where we say, let's first break up our data into sort of a training set and a validation set. And this will let us know, based on what our model has learned, will it actually generalize to new information? So back to Kaggle. Thankfully, Keras gives us a very easy way of doing this. Sometimes we'll like split up our data manually, but Keras actually makes this very, very nice, where all we have to do, this is the same model, and it's the same call to fit, and all we're doing is passing a parameter called validation split. And so validation split says, this percentage of the training data I want you to use as validation data. And so this will be data that our model never sees, never actually gets trained on, but does use. And let's see. I'm sorry that I'm going brain dead. But there was something that I wanted to check. Okay, cool. We're back. My brain fart is done. So we pass validation split equals 0.01. That just says hold 200 of the images back just so we can test our model. So if we run this, I have again picked a different batch size, which I don't know. I guess I just pick batch sizes randomly. Actually, let's see. What was our batch size up here? Did I crank it down to 16? I think I did. Yeah, let's call it 16 again. And then let's actually give it 50 epochs as well. And you know what? I don't need the verbosity. I don't need our notebook getting filled up with training logs. It's kind of fun to see, but at the same time, there's a lot of scrolling involved, you know? But so now jumping ahead while we're watching it do this, we can plot our loss, but also our validation loss. And then we can add a little legend that just shows us what color is what in the upper left. And as soon as it finishes, it's thinking about it. Oh, now I'm wishing I had turned verbosity on. Verbosity, it's not really a computer science word, but it's a word that computer scientists use a lot. Okay, so now we can run this, and interesting results. So I don't really know what to make of this, besides the fact that it seems like generally our model is generalizing pretty well. That it is able to predict with sort of relative accuracy on things that it has not seen before. And it does seem like, I mean, again, most of this training doesn't actually seem to have been that valuable. It seems like we learned a lot in our first like 4 epochs. And then, yeah, on average, we're going down, but there's sort of a lot of noise. So to finish the dense neural networks off, and then we'll actually try to generate some predictions. Ooh, we got like 10 minutes left. So the experiment that I was going to propose is that we actually put our entire training loop here. So this is all of what we need to do to train our network. And I was just going to do it for 20 epochs, and just basically be able to pass in an arbitrary. So someone asked, it was Michael that said, or no, it was not Michael. It was Nanotubular who said, yeah, I can never know how big to make my layers or how many layers to do. And the answer is that is like a really tricky question. And like, yes, people have done many PhDs just trying to answer that question in sort of a different way. But one thing that you can do is you can just test out a lot of values for this. So this function accepts an n that is sort of the length of our neural network layer. And it can spin up a model with that number of units. So our middle units here is just that n that we're passing in. And then do the whole training cycle. And then just return the history of that training cycle so we can grab performance data. And I'm going to take out the first layer here. So we're just going to look at, maybe we could look at, remove that. We're going to look at what if we made it 128, what if we made it 512, and what if we made it 2048 or 2048. In fact, let's make this even smaller. Let's say, what if it was 32? What if it was real small? Excuse me. Okay, you know what? Actually, I was about to. Okay, we're gonna table this for now. What I want to do actually is just submit some data or make a submission based off of this because it seems like we actually really have made some progress. So I want us to take our model from here, and we'll have to prep our test data. So we can actually come and grab where we did this for our training data. So let's grab this cell right here. To get our test input data. So after training, let's add taking predictions on our test data. So instead of importing our training here, let's import our test data into testdf. And then we can iterate through, and all of our images should be there. And so we can put those into test image data. And that was pretty quick. So there are only 120 images in our test data. And then I'm going to be doing a lot of scrolling back and forth because basically whatever we did for our training data, we want to do for our test data as well. And I believe we just turned our input data into an array. Okay, yeah, so we're skipping our experiment for now. So we're turning our test image data into our test input data. And then if everything has gone correctly, we should be able to just take our model, call predict on it, and pass in our test input data. And this should give us predictions. Oh, okay, we're facing some issues. It says unexpected result. Please use model.compile. Interesting, but didn't we already compile our model? We ran model.compile, and we trained it. Oh, yes, good call. Test image data. 10 points for Savarna, because that is totally true. I don't know if that was actually our issue. Oh, maybe it was actually. Maybe we were just passing an empty. Yeah, that was totally the one. Okay. Everybody claps for Savarna. Usually it's Polar Void's job to catch my bugs, but well done. So now we can just take a look inside our predictions, and we have some predictions, and a lot of them seem very negative, which is interesting, which is maybe something that we look at later. But some of them are not negative. We have some of them are like 3 or like 5. But let's submit this and see what it does. Let's see if we get better results from this. We might even say we know that nothing can cost less than 0. So it might even be interesting to say like like clip this at 0. But for now, let's just take these predictions. We'll take our test df, and we'll say our prices are just this now. Does that work? So now if we just look at our test df as a whole, great, we have a price column, and all we need out of this are just the ID and the price. This is our submission df. And then submission df, we can say to CSV as submission.csv, and then we can say index equals false. So we want to check. Srivanik, thank you for giving the claps. I appreciate that. Hats off for Savarna. So if we come in, we see our submission CSV. If we want to just double check, we can download that just to be sure. And if we open it, cool. It looks, I mean, the fact that we have negative numbers is something that I think is just like interesting to dive into and see, see what's going on. But we have lots of numbers that seem like, okay, like 4 Ethereum, 1 Ethereum, 0.8 Ethereum doesn't seem crazy. So let's actually submit this and see what happens. And I'm going to, for the time being, comment this out just because it'll make our submission run longer. But if we try to submit, I really let time get away from me there. This should not take too terribly long to submit if we don't have any bugs. And honestly, we were doing a lot of little experiments. We were going down a lot of little tangents. So I wouldn't be shocked if there was a bug involved. Let's see. Are we getting any interesting logs? No logs yet. Oh, we got some logs. Cool. Importing all of our photos. That's when we double checked to see if our things were the same dimension. We're getting a little warning. And Eugene, I don't know if you were following along and already submitted and checked, or if you just have a lot of confidence. But either way, I appreciate it. Let's check. Actually, has anybody beat me to the punch and entered the leaderboard? Okay, no one yet. This is actually a downside of doing the verbose output, that when it gets slurped up by log programs, it can not really get formatted correctly, which is tragic. Also, I don't even think this is we really should have commented out all of our training loops that are not our like final one we're using, because like, oh yeah, right now we're just spending time waiting on the training of a model that we're not going to use. Okay, yeah, I think this is the one that we actually end up using, the one that has 50 epochs. This is my idea of a good time. It's just watching our malformed Keras logs come through. I think that was our final model, the one that was 2 million. So maybe we'll make some predictions. Fingers crossed, y'all. Oh yeah, okay, so here's our test data. This is us importing our test data. We could have also written ourselves useful logs ourselves. We could have printed out, like, now we're doing our test data. Srivanik, thank you for the fingers crossed, yeah. And did it go? Do we have we have our submission. Do we get a score though? Or do we have any errors? Successfully ran. Okay. Wait, I feel like normally it actually comes up as a submission. I guess we can come back here and click on complete submission. There we go. And oh, that is tragic. That is very tragic. 38.2. Interesting. Okay, well, that's kind of sad. Ooh, y'all. Okay, this actually might be on me. I'm gonna double check. Well, okay, so first of all, this is a little bit better. You can see it's not terrible. It could be worse. but this is a little bit suspicious to me, and it makes me wonder if there might be something wrong with the test set. And if there is, I will fix it and I will let you know. But I guess we'll just leave it on, hey, technically, this is a better score. 38.2. Oh, okay. So someone actually did get around 38.2. But I guess the thing that might be true based on how this is going is our test data set might be genuinely different from our training data set. And if that is the case, then I want to fix that problem. And there might be a very simple fix that is in my head that I can't reveal. But we'll really quickly wrap up because there might be a stream after this. It has been a blast having you here. Thank you so much for participating. I will drop the check-in and feedback form links one last time. Get credit for being here. Remember the 5 ways that you can get a swag drop are being the top 2 scorers, submitting anything, and being a contributor. So if you have a little blue next to your profile, then that means you're a contributor. If you're not a contributor, it's very easy to become one. The 4 things you need to do, we can just go to Kaggle progression. Progression, there we go. If you are not a contributor, the 4 things you need to do to become one are run a notebook or script, which you've probably already done, make 1 competition submission, which you've probably already done, make 1 comment, which you're welcome to do just on our discussion page. If we go to the cat and we go to discussion, you are happy to jump on here and leave a comment and give somebody an upvote. And then you'll become a contributor and be eligible for the swag drop. The other 2 are you can try to foster a discussion if you have any questions or respond to folks. So, everybody that has started a discussion here is in the running for that. And then finally, if you have code you want to publish, if you publish your code, you can be in the running for that swag drop. So those are the ways that that you could win some swag. Thank you so much for being here. Tomorrow, hopefully I'll have an update on maybe unbreaking this competition. But then definitely we will dive into convolutional neural networks is our big thing for tomorrow. We might look at ensemble networks, and we'll close in on the end of our competition. Oh, no worries. So this is on Kaggle, yes. And to become a contributor, these are the 4 things you need to do. It is run a notebook or script, which I think you've probably already done. Make a competition submission, so submitting this competition counts. Make 1 comment, so like on the discussion, make a comment, and then give 1 upvote to anything, either a notebook or somebody else's comment. And I can drop that link here. And this is on Kaggle, correct. We will not look at random forests for this. Random forests are great for tabular data. Random forests work not as well on image data. Although, I don't know, it could be fun. If we just have extra time in the last day, maybe we'll do some random forests for fun. All right. Well, thank you so much for being here, y'all. Happy Wednesday. Happy Global Hack Week. And I will see you tomorrow. Take care.